Now, for understanding the phasor representations of RLC circuits, we will study the phasor diagram for individual elements under alternating excitation. So one by one we will draw the phasor diagram of the voltage and currents for a resistive circuit, for an inductive circuit, and for a capacitive circuit. And we will consider or assume that during those three different circuits other elements are absent. That means we will consider one circuit with pure resistance, that is, there is no other inductive component or capacitive component, so reactive component will not be there. And also we will consider one inductive circuit where we will assume that capacitive element and resistive element will not be there. And at last we will also consider one circuit where pure capacitance will be there, so there will be no resistive element or inductive element. And we will study the phasor diagram for these three distinguished circuits. So let us start with the pure resistive circuit. So let us consider the Vs, which is applied, is given by Vs equal to Vm sin omega t. So it is considered that one sinusoidal voltage is applied across a pure resistive element whose resistance is R. Now let us consider the voltage across the R, that means the voltage drop across R is VR. So here we will see that the current passing through this resistance, if it is IR, so the source current and the load current will be same because it is a series circuit. So we will see that I equal to IR for this case. And now we have to draw the phasor diagram for this pure resistive circuit. Now, as a rule or the convention, we will start with fixing the reference. So we have to fix a reference phasor. So let us consider the reference phasor is our current, and we will see that if we are going to draw the phasor diagram for any series circuit, it is good to take the current signal or current phasor as a reference, because in series circuit current remains the same through all the elements. So if we take the current phasor as a reference phasor, so it will be easier for drawing the other phasors. Though taking the voltage phasors as the reference phasors also, it is possible to draw the phasor circuit, but if we take the current for series circuit, it will be easier. So now if we represent this arrow as our current phasor, that is I equal to IR, so now we have to draw the voltage phasor. Now we know for resistive circuit the impedance of the resistance is equal to the resistance itself, and voltage drop across the R is frequency independent, and it is nothing but IR, and hence the phasor will be lying in the same phase with the current, because the phase displacement for the voltage and current for a pure resistive circuit is 0. So this is our phasor diagram. Now if we go for the time diagram, so if we want to plot the instantaneous values for this voltage and current waveform as a sine wave, so we will see that if we have our omega t axis and amplitude axis, so we can put the V along this. So we will see that this is our voltage, say Vs, and the current will be somehow like this. That means the current IR will be in the same phase. So they will start together, they will go maximum value together, and they will again become zero. They will go negative maximum together, and they will follow each other. So they will be in phase. So this is about the time diagram of, or waveform diagram of, the voltage drop across the R. So this will be VR, and this is the IR, so voltage and current. Now here we can see that the resistive circuit doesn't make any phase displacement between the current and voltage. Now let us see what happens in case of one pure inductive circuit. So as we have drawn, the inductive circuit is also being excited by one alternating voltage source. Same voltage is this V will develop which conducted. Now due to the conduction of L, the inductor will develop its own impedance called ZL is equal to J omega L, and this omega L is nothing but is denoted by XL, and this XL is called inductive reactance. So this is the the circuit it is also known as inductive reactance. Now is VL, cell is VL, and we have to draw the Phasor representation between I equal to IL and the VL. So for this series circuit also we will assume or consider that I equal to IL is the reference phasor. Now as for inductance, the current lags behind the voltage with an angle 90 degree. So VL will be drawn by rotating 90 degree in anti-clockwise direction. As we have already studied that or discussed that if we find any vector from a reference vector after rotating in anti-clockwise direction, then that vector will be called as the leading vector. So we are getting, or if we are moving in anti-clockwise direction for searching the VL, we will find it after 90 degree phase displacement for the case of pure inductor. So this is the Phasor diagram of pure inductor or pure inductive circuit. Now for the instantaneous waveform, instantaneous values, the time varying waveform, if I want to draw to see the instantaneous values, so we have to draw the amplitude axis and the omega t axis. And if we have drawn so in time varying waveform, if this is the current through the inductor IL which starts from 0. Now if the sinusoidal waveform drawn here represents the current waveform for the inductive circuit we discussed, then the voltage waveform will start at the point pi by 2 at the left hand side of the origin 0. So By convention, the leading phasor or the waveform for a leading quantity should start before the reference starts. So if the reference is lagging quantity, here as we consider that IL, so VL will be leading over the current IL. So we will see that there is the phase displacement of 90 degree at each point. So here also we will see that this angle displacement is say 90 degree if it is assumed to be 90 degree. So now we understood that through one pure inductive circuit, the current through the inductor and the voltage dropped across the inductor, that is VL and IL, they will be separated by an angle equal to pi by 2, where the voltage will be leading over IL. Now if we consider the other circuit, that is one pure capacitor is connected across the Vs, then also current will be produced, and that current will be say denoted by IC, and we will start drawing the phasor diagram with the reference, which is nothing but I equal to IC again, because it is also series circuit. So we will be drawing the phasor of the voltage, which is Vc across C, by the convention, by considering the convention, that is the voltage dropped across the capacitor lags behind the current through the capacitor. So Vc will be lagging behind the IC by one angle pi by 2, and this lagging phasor will be drawn after rotating in the clockwise direction by convention. So if we want to draw the time varying waveform with the help of omega t and amplitude axis, so this is V, then again if we draw one sinusoidal waveform for representing the reference IC, we will see that the voltage waveform will also start after pi by 2 angle. So as the signal is starting after pi by 2 angle from the origin, so this signal will be called as lagging signal, and which will be denoted by Vc here. So this is Vc and this is IC. So here we can see that the phase displacement is also pi by 2 in the time diagram. So in this way we understood the behavior of pure resistor, pure inductor and pure capacitors when they are individually excited by one sinusoidal voltage source. So we understood the phasor diagrams, we understood their phasor representations or phase angle displacement when they are represented in time varying waveforms.